Hi folks, and welcome back to Math with Captain Rod. The purpose of this video is to demonstrate how to solve a second order differential equation, or at least one way to solve a second order differential equation that has the following conditions. We're going to look at the equation d squared s dt squared equals 3/8 t, and ds dt needs to equal 3 when t is equal to 4, and s needs to equal 4 when t is equal to 4. So we're looking for a function that satisfies all of these criteria. Now, first step here, what I'm going to do is just anti-differentiate both sides of this equation. Now this is, think of it like this. This is s, and then you can think of this as an operator. This means differentiate s twice. If I anti-differentiate this, we're down to just ds dt equals right-hand side. When we anti-differentiate this side, we're going to get 3t squared over 16. The 16 is coming from, right, we're adding 1 to our power, so the 1 became a 2, divide by the new power. When we put a 2 in the bottom, keep in mind there's already an 8 there, they would multiply to 16. Now, I've anti-differentiated, which means we have to add a constant to this, and I'm going to call that constant C1. Now, the reason I tacked a 1 on is because this equation is still a differential equation. It's got a derivative. So we're going to anti-differentiate again. That's going to introduce another constant. So when we anti-differentiate this again, this is going to read s equals 3t to the third over 48. Now, this 3 came from adding 1 to the power. And then when you divide by your new power, if you put that t downstairs, the 16 times 3 will become a 48. You could also leave this just 16 times 3, and they're going to cancel anyway. But all right, let me move on here. So C1, when we anti-differentiate C1, we get C1t. And because we, again, have integrated both sides or anti-differentiated, we're going to introduce another constant here. So two constants get introduced in this problem because we've anti-differentiated twice, and they're different constants. That's why you need the 1 and the 2. So what we have now is a whole family of functions that will satisfy this. Now we're going to go through and apply these conditions here. So ds dt has to be 3 when t is equal to 4. So I'm going to look at this equation for ds dt. And this is now going to read 3 equals, so that's for this, 3 times t squared over 16, where t is 4, so 4 squared over 16, plus C1. So this line is coming from taking this equation and putting 3 in for ds dt and 4 in for t. Now, 4 squared over 16 is 1, so this is going to read 3 equals 3 plus C1. If you solve this, you get C1 equals 0. Now I'm going to apply this condition on S. When t is 4, s needs to be 4. So I'm looking here, my equation for s. I'll go ahead and write it to the right. So we're going to have 4 equals, and that's for this. And I'm going to do this here. So this 3 over 48 ends up being 1 over 16. So I'm going to write that 1 over 16 t to the 4th. So that's going to be, I'm sorry, third. 4 to the third. Okay, plus C1t. Well, we already know that C1 is 0. I'll just put a 0 there for placeholder, plus C2. And again, the 16 is coming from, if I take 3 divided by 48, that's 1 over 16. I just wrote it in a little bit simpler format. All right, so now 4 equals 4 to the third over 16, I believe is 4, plus C2. If we solve this for C2, we get 0. So the function we're looking for is just s equals 1/16 t to the third. And that's this function. I just reduced the 3 over 48 to 1 over 16, and the values for C1 and C2 are 0. So I hope this video helps demonstrate how to use integration to solve a appropriate type of second order differential equation. Have a great day.